So the single sample t-test that we learned about in the preceding video, that's helpful in situations when we have a reference mean. But actually, we don't usually have a reference mean. In ordinary circumstances, we have two samples whose means we'd like to compare with each other. And in that case, we use an independent t-test. All right, so to have some fun with independent t-tests, let's talk about penguins. What's more fun than penguins sliding around, having fun in the snow? So we're going to load a data set from the Seaborn library called Penguins, and we're going to use this drop NA method to remove any rows that are missing data. That'll just make it easier to work with these data. So there we go, we've loaded it. Let's have a look at it. We've got 343 rows of data, but after removing 10 rows with missing information, we only have 333 left over. And so we have a number of different species of penguins from different islands, I assume near the Antarctic or maybe even in the Antarctic. And we also have different sexes for those penguins. We have body mass measurements in grams. We have flipper length measurements in millimeters. And we also have measurements on their bills. I guess those are their mouths. We have length and depth of their bill. So yeah, so lots of fun data for us to play with here and do some comparisons. So let's have a look at what species we have here. Okay, so we've got three species, the Adélie, chinstrap, and gentoo species of penguins. And after cleaning up our 10 rows with missing information, we have 146 Adélie penguins, 68 chinstrap penguins, and 119 gentoo penguins. So we can, for example, create a new data frame. So we've got a data frame here. We can create a new data frame with only the Adélie penguins by specifying that we only want the species that are Adélie penguins. So now when we look at that data frame, we can see, yep, we have 146 rows corresponding to the 146 Adélie penguins. Otherwise, the information is largely the same. We've just subset down to those particular penguins. And let's have a look at some information on what islands those Adélie penguins come from. So we've got three different islands, Biscoe, Dream, and Torgerson. And we have 44, 55, and 47 penguin measurements from each of those islands in that order. And let's also look at the gender data or the sex data. I guess penguins don't have gender really, but we have an even number. We have 73 females and 73 males. Now we can take a look with a snazzy box plot to see some of these different variable comparisons. So we can look at body mass index as a function of sex, as well as a function of the island that the penguin is from. So clearly we can see from the box plots that the weight of the males tends to be higher than the weights of the females. But it isn't obvious to me that after controlling for sex, the weights vary much by island. All right, so now let's test if this apparent difference in male and female mass is statistically significant. In order to do that, let's get all of the weights, all of the body masses of the female Adélie penguins into a vector called F. So I'm doing a few things here, right? So I'm taking our Adélie data frame here, our pandas data frame, and then I'm subsetting to females only, and I'm grabbing the body mass column from that data frame, and then I'm converting all of the values to NumPy. So I'm taking a pandas series, converting it into a NumPy array, a vector, and I'm also dividing by 1,000 because the body mass was in grams, but they're just really big numbers. I think it's easier to read if we do it in kilograms. So I divide by 1,000. All right, so that gives us our female body masses, our female weights. And then let's do the same thing for males. So everything about this line of code is the same, except that I changed female to male here. All right, so we can calculate the averages pretty easily. So we can calculate the mean of our females, call that F bar. So the mean female mass is 3.37 kilograms. And the mean weight of the male penguins is 4.04 kilograms. So that seems quite a bit heavier. If we want to quantify whether this heavier measurement for males relative to females is statistically significant, then we can use Welch's t-test. Nothing to do with the grape-related company that makes juice and jam. Nope, it was devised by the 20th century British statistician Bernard Lewis Welch. Here is that calculation. It is actually quite related to the t-test that we saw earlier. So earlier in this notebook, we had the t-test here, which was an obvious derivation of the z-test. And so the independent t-test that we're working with in a second is similar to this. So instead of subtracting a reference mean, we're going to subtract the mean of another sample. And instead of the standard error of our single sample, we're going to have to come up with something a bit more clever for what the standard error is in the denominator. All right, so back to our penguins and our t-test. We've got, okay, our t-test is here. So as I said, we subtract one of our sample means from the other, and that's our numerator. And then in the denominator, we have our sample variances over our sample sizes for x and y respectively. We add them up and then take the square root. So that isn't too far off the usual standard error calculation for a single sample, but we're pooling together the two standard errors in a way here. So that's your Welch's t-test. So we're going to work through a code demo in a second to actually calculate the t-value. But I want to take a quick note here that student of the single sample t-test fame, the Guinness brewer, he also had an independent t-test. And that is, even today, markedly more popular than Welch's t-test. But students assumes equal population variances, that the variance underlying the distribution of x is roughly equal to the variance underlying our second distribution. And so that makes it less robust. In case you're curious though, student's formula is the same as Welch's, except that it uses something called pooled variance in place of individual sampled variances. And you can read about that more by following this link. All right, so that note aside, let's actually calculate the t-value here. So we already have our means, f bar and m bar, instead of x bar and y bar. And so now we need our variances. So we can calculate the variance for the females here, the variance for the males here. I am setting the degrees of freedom equal to 1, which is, technically the correct thing to do. But again, it's not going to make very much of a difference with these large sample sizes. And yes, our number of samples of females, our number of samples of males, we can use the size argument on our NumPy arrays to get those quickly. And now we have all the pieces of the puzzle. We can simply do the calculation. So here we have x and y, but we're going to do the same thing with f and m for female and male. So in our numerator, f bar minus m bar, and then in our denominator, the analog of what we have here, but with f and m instead of x and y. So that will give us our t-value. It comes out to -13. And I have enough experience that I know at a glance that that is a big t-value and it's going to be statistically significant. But let's calculate it anyway. So if we want to calculate our p-value, we're going to need to know what our degrees of freedom is. And we can estimate the degrees of freedom in this situation using something called the Welch-Satterthwaite equation. So you can click through and get more detail on that, but I'm not going to go into the detail. It doesn't really matter too much. You just need to know how to apply it. So it's this big chunky equation. It gives us a way to estimate the degrees of freedom for the Welch's independent t-test that we're using now. So here is the formula. And we can put it into action here by passing in the variance of our two samples and the number of observations in our two samples. And so we get an estimate of 135.7 degrees of freedom. So now, with all of that information, we have our t-value, we have our degrees of freedom. We can pass that information into the t-distribution calculator that we already created earlier. So we could simply use this code here. I think that's actually a lot simpler. So we've got our -13, our degrees of freedom, and with the way that I'm calculating things here, we do need to add 1 extra degree of freedom to get exactly the correct value. Again, it's not going to make much of a difference if you do that or not. Either way, you get this p-value of 6.4 times 10 to the -26. And that is an absolutely monstrous p-value. This is extremely close to 0. So remember, our threshold is it less than 0.05? And this is so much lower than 0.05. It has like 25 zeros before we get to a 6 after the decimal place. Converting that into our negative log p notation, that's a negative log p-value of 25. It's an absolutely monstrous p-value. It means that we have an extremely statistically significant difference between the weights of the male penguins relative to the female penguins. And yeah, of course, you probably wouldn't want to typically go through all of these steps to calculate your t-value and p-value. So you can use the built-in independent t-test method, and you will get the same value as we did. So you pass in your vector of one of your vectors, and then you pass in one of your other vectors. In this case, it's our female weights and our male weights. I'm setting the assumption of equal variance to false so that we use Welch's independent t-test instead of Student's variant. And we get the same t-statistic of -13 and the same p-value of 6.4 times 10 to the -26 as when we did it in more steps ourselves. All right, so there's your first taste of an independent t-test. Up next, I've got a variant of an independent t-test that we can use in special situations.